Okay, so yesterday we were talking about supremum and infimum of a set, right? So what is supremum of a set? Supremum of a set is least upper bound. So
Least.
Sir, you are not audible.
Least upper bound of a set.
okay, can you hear me clearly?
Yes.
Yeah, sir.
Okay, so A is a non-empty set and real number U is said to be least upper bound, right? If it is upper bound and all other elements are any other upper bound is greater equal that least upper bound. So supreme is also called as least upper bound is called as supremum of a set, right? And also we define greatest lower bound. So A is a non-empty set, right? And V is greatest lower bound if V is the lower bound, and if there is any other lower bound, then it is less equal greatest lower bound. So greatest lower bound is called as infimum of a set. Right. So we discuss about supremum infimum in detail. Right. Now for example, if so let A is equal to set of numbers. So if you look at set of numbers of the type 1 by n, now what are the elements of this set? 1, 1 by 2, if n is a natural number, so n varies over natural number, so 1, 1 by 2, 1 by 3, 1 by 4, right? So these are elements of this set, all such elements. Now, if you see these elements 1, 1 by 2, 1 by 3, so 0 is here. So is 0 is member of set A? Is 0 member of this set?
No.
Right. So 0 is not member of this set. But everything, so all such type of numbers are in this set. Now, what is supremum of this set? So prove that.
Sir, if we take n equals infinity, then?
Where is infinity? Is infinity natural numbers?
Oh, yeah, sir. No, sir.
Right. So prove that supremum of A is equal to 1. Right. So supremum of A is 1 and infimum of A is 0. So how to prove this? How to prove this? So to prove that first part, so to prove supremum of A is equal to 1, right? So first prove that 1 is upper bound. Of set A, right? So first prove that 1 is upper bound. So why 1 is upper bound?
All elements are less than equal to 1.
So note that for each natural number, n is greater equal 1, right? Every natural number is greater than or equal to 1, right? So every natural number is greater than or equal to 1. Therefore what you can say about 1 by n, right?
1 by n is less than equal to 1.
Therefore 1 by n is less than or equal to 1 for every keep your mic off. Somebody kept mic on. Please keep your mic off. So every natural number is greater equal 1. Therefore, for every natural number n, 1 by n is less equal 1. That means every such type of element 1 by n is less than or equal to n. That means for every element of A, that element is less than or equal to 1, because for every such type of element 1 by n is less equal to 1. That means what are the elements of set? Elements of set are 1 by n, and therefore every such element, that means every member of set A is less than or equal to 1, right? Hence 1 is upper bound of A. So 1 is upper bound. So next, 1 is least. So why 1 is least upper bound of A? That means if you choose any number smaller than 1, so if I choose any u less than 1, then u is not an upper bound of A. Is it true? So is this true? If I choose any number,
Yes, sir.
Yes.
right? Because if u less than 1, then x is equal to 1 is a member of A, and that x is greater than u. Right, 1 itself is a member of set which is greater than u, so therefore you cannot go below 1. So therefore hence 1 is the least among all upper bounds of A. Therefore supremum of A is equal to 1. Now secondly, so to prove infimum of A is 0. So first part is 0 is lower bound. So 0 is lower bound, it is obvious because note that our previous knowledge, right? Previous means whatever we discussed about real numbers. So for each natural number is positive. In fact, it is strictly positive. Each natural number is positive, and therefore we know that if number is positive, its inverse, multiplicative inverse is also positive. So 1 by n is also positive, right? For all natural numbers. So if real number is positive, its multiplicative inverse is positive. So natural number is a real number and it is positive, basically strictly positive. Therefore, its multiplicative inverse is also positive, right? So that we know by general properties of real numbers. And hence, every such number 1 by n, for natural number n, every such number is greater than 1. Therefore, for each x belongs to set A, x is greater than 0 or greater equal 0 you can say, but it is strictly greater than 0. Therefore, 0 is lower bound. 0 is a lower bound of set A. So this is clear. But by why 0 is greatest lower bound? Now 0 is the greatest lower bound of A. So why 0 is the greatest lower bound? So if you 0 is here, 0 is not member of set, right? 1 is here and 1 is member of set. So if you choose any u greater than 0, so how to prove that 0 is the greatest lower bound? 0 is lower bound, that is clear. But 0 is greatest among all lower bounds, right? That is any number greater than 0 is not a lower bound, right? So why any number greater than 0 is not lower bound? So let us check this. So let u greater than 0, let u greater than 0, then what happens? 1 by u is greater than 0, am I right?
Yes, sir.
Right. Then, so what is our aim? Ki if I choose some number u greater than 0, then this is not lower bound that I want to prove. That means if you choose any number u greater than 0, immediately I can see that there is a number, right, which is in set A. There is immediately we can produce a number which is less than u and which is member of A. Correct? This is our aim. Ki there exists some number of element of set A which is less than u. So how to visualize, how to produce such element?
We can consider 1 upon u plus 1.
But 1 upon u plus 1, what is the guarantee that it is in A? Right?
As u is in the set of natural numbers, u
No,
plus 1 must be in,
I am not saying
must-
u is natural number. U is just real number greater than 0. Right?
so can we write u is equal to 1 upon alpha so that it would be easy to prove?
Whatever is 1 upon alpha, u is just real number. Right? Suppose my u is uh, 3 upon 51, for example. It is greater than 0, right? Now, so here I have 0, here 3 upon 51, right? So this is not natural number. So what is a number here which is 1 by n, which is less than this u? That is the problem. Clearly, 1 upon u is positive, right? I don't know what is 1 upon u, but whatever it may be, I know u, so I know 1 upon u, but how larger is that doesn't matter. Correct. So, see, try to observe these things carefully, because if I choose u is equal to 1 upon 500, right? So here 0 and here u, and what is u? 1 upon 500. It is very small number. So what is 1 upon u? 500. Right? Certainly it is greater than 0, no doubt, because u is greater than 0. Now u is 1 upon 500. But if my u is 3 upon 523, for example, then what is 1 by u? 523 divided by 3. What is this number? What is this number? If you divide by 3, then 1
131.
uh,
Oh no.
174.
170.
4.1. No,
Right.
174 point something.
Whatever it, 174 point something, whatever it. So if u is 1 upon 500, then 1 by u is this. But if u is 3 upon 523, then it is 174. So what is the main point? If you choose a real number greater than 0, 1 by u is a real number, right? So whatever u, 1 by u is real number which is positive. And if I choose particular n, which is 175, right? Okay, forget about this u. I am choosing u is equal to 3 upon 523. 3 upon 523. This is my u, and I am looking at this is my u. I am looking at 1 by u. 1 by is 174.1, and if I select n naught is equal to natural number. Now I am looking at natural number. 1 by u is not natural number, or u is also not natural number, right? U is 3 upon 523. 1 by u is this number, which is some bigger number, which is 174.1 something, which is not natural number, but I am looking at natural number which is next to this real number, 174.1. What is the next natural number? 175, or you can select 176 also, or 180 also, no problem. So is it clear what I am doing? I am looking at this. Now what is 1 by n naught? What is 1 by n naught? 1 upon 175, right? Am I right? Whatever I am writing, is it correct?
Yes, sir.
Okay. Now, is this member of set A? 1 upon 175. Is it member of set A?
Yes, sir.
Yes, sir.
Now what is the relation between 1 upon 175 and u? Which is bigger?
Sir,
U is greater.
1.
U is greater, right? And this is greater than 0. So I can produce element from set A which is less than u. Do you understand what I am doing? Observe this process. What process I did? Is it clear?
Yes, sir.
So if you select n u greater than 0, look at 1 by u, which is positive number. Choose natural number greater than 1 by u, and the corresponding element 1 upon n naught is the required element which we wanted to produce, right? So if you choose u greater than 0, then what is our aim? What is our claim? What is my claim? What is my claim? If I choose u is a lower bound, 0 is lower bound, no doubt, but we want to prove that any number greater than 0 is not lower bound. That means if I choose u greater than
There,
0, right? If I choose
there,
u
ex-
greater, Right?
There exists a number in set A which is which is smaller than u.
Right. So if I choose any number u greater than 0, then my claim is u is not lower bound. This is my claim, because if I prove that no number greater than 0 is a lower bound, that means 0 is the greatest lower bound. Or already we have verified that 0 is a lower bound. And any number greater than 0 is not lower bound, that means 0 is the greatest among lower bounds. Right, that means if I choose any number u greater than 0, u is not lower bound. That is, what is my claim? If u is greater than 0, then u is not lower bound. U is not lower bound means there exists some member in set A such that x is less than u. Right. So if you choose any number greater than 0, immediately if you can see that key elements from set are less than u, that means you cannot be lower bound, because if u is a lower bound, all members of set should be greater than or equal to u, but that is not happening. That we want to prove. Okay, so this is our claim actually. Right. So what is our claim? If I select u greater than 0, there is a number x element in A which is less than u. Okay, so and what is the procedure? This I did for particular u. Here on right side I did for particular u now, and then I can produce some number 1 by n naught which is a member of set which is less than. So how to make these generals? So since u greater than 0, 1 by u is greater than 0, right? So choose natural number choose a natural number n naught, because I am choosing particular, such that that natural number is strictly greater than 1 by u. Right? I am just choosing natural number. Then what about 1 upon n naught is less than u, and 1 upon n naught is member of set. Do you agree with this? Do you agree with this?
Yes, sir.
Right.
Yes, sir.
So I am just looking at 1 by u and I am choosing natural number greater than that. So which natural number you choose, any, doesn't matter. For example, in this particular example, if I were selected n naught is equal to 180, then I will look at 1 upon n naught, 1 upon 180. Is it a member of set A?
Yes.
Right. And 1 upon 180 is also less than u. Right. So similar situation arises. So you choose any number greater than 1 by u, that will fulfill our requirement. Thus x is equal to 1 upon this particular element is in A, and 0 less than x less than u. Therefore u cannot be lower bound of A. So u cannot be lower bound. So if you choose any number greater than 0, that number cannot be lower bound. Hence 0 is the greatest lower bound of A, and therefore infimum of A is equal to 0. Okay, so this is clear. This is clear.
Yes, sir.
Now the question is how what is the guarantee that given any real number there is a natural number greater than that? That will prove later on, which is Archimedean property of real numbers. And Archimedean property is very essential because that guarantees that there is a natural number. Given any real number, we can produce natural number greater than that. That ensures such n not exist. Right. So let us work out one more example. X such that 1 less than x less than 2. Right. So prove that. Prove that supremum of A is equal to 2 and infimum of A is equal to 1. Even they are not members of set A, but supremum infimum exists. So what is the first step to prove supremum of A is equal to 2? This we want to prove. So in that, what is the first step? 2 is an upper bound of A. This first you should verify, and that is clear from the definition, right? So we have for every member of set, right? All members are in fact all members are less equal to, in fact all members are less than, because if you see the definition of set, it contains all the real numbers less than 2 and greater than 1. So every member is, so that is clear, right? Therefore 2 is upper bound. Now next step, 2 is
Sir,
right. Yes.
sir, x is strictly less than 2 na?
Yes, strictly less.
And you wrote is less than or equals to 2.
So 1 is less than 3. So I can always write 1 is less equal 3. No problem, because when I say less than or equal to, either less or equal, if one of them is true, then that is fine, no problem. Because why I am writing less than or equal to? Because what is our definition of upper bound? Ki U is upper bound if every member of set is less than or equal to U. That is our definition. So inconsistent with our definition, I am writing less equal, and which is not a wrong at all, right?
Yes, sir.
So because we have a definition like this, so to be consistent with definition that I am writing, otherwise you can say that it is strictly less, ultimately is upper bound, that is also right. Okay, so now 2 is the greatest, least upper bound. So this we want to now verify. So what we want to prove basically, that is what is our claim. No number smaller than 2 is an upper bound of A, right? What I want to say, 2 is the least upper bound means any number that is, if U is less than 2, then U is not an upper bound of A, right? So you need to understand these equivalent statements. I am writing a same statement in different words so that you can understand what actually we should do. So 2 is the least, that means you cannot go below 2, right? If you try to go below 2, that number will not remain an upper bound, right? That is, if U is less than 2, right? This is our claim. I am not saying number smaller than 2 is not upper bound. I am not saying it. This is my claim. So if U less than 2, then U is not upper bound means what? When we say that u is not upper bound,
There exists an element of A greater than U.
so we can see that there is x in A which is greater than u. That means some members of set are greater than u, so you cannot be upper bound. So there exists some element in A such that x is greater than u. So one element is sufficient, right? At least one element from set is greater than u. That is sufficient to say that u is not upper bound. So this is what we want, right? So how to start now? You prove that 2 is the least upper bound. So this we want. So how to start? Logically, the idea should be clear. How to start?
We'll consider a U less than 2.
Right. Very good. So how to start? First of all, choose any number, no matter what. Just close your eyes and just choose number smaller than smaller than 2, not any special element. Whatever. If I select element which is 2 minus 10 raised to 5000, 10 raised to minus 5000, then it is very close to you. Then also we can produce some member of set greater than that number. So let u less than 2, right? If you choose, if somebody gives you any number smaller than 2, then you should be able to produce x greater than u, right? Because suppose your claim is that, right, logically what we are doing, your claim is 2 is least upper bound, and suppose somebody do not accept this, right? Then what you will do, you will ask him ki give me any number smaller than 2, I will prove that that number is not upper bound, right? Is it clear what I am saying? Ki somebody do not agree, do not believe that ki 2 is not least upper, 2 is least upper bound. So what you will do? You will ask him ki give me any number smaller than u. I will prove that ki that number is not upper bound. That means give me any number smaller than 2. I can produce element in the set greater than u. So let u less than 2. What we want? X in A is greater than u. This we want. Okay, so here is u, right? For simplicity, I am saying that there is some, so u is less than 2. So there is some space between u and 2. There is some space between u and 2. Correct? Now, what is the number x in the set? Then, what is the number x which is a member of set and which is greater than u?
Sir, can we consider arithmetic mean of U and 2?
Right, very good. So this is the simplest choice. There are many, but what is the simplest choice? Right, without loss of energy and time, we can easily produce, right? Then u is less than u plus 2 by 2, mean of this clearly. Am I right? Therefore, x is equal to u plus 2 by 2. Is it member of set? Is it a
Yes,
member?
sir.
Yes.
Again, there is some ambiguity. What is ambiguity? Because as a mathematics student, you have to take care of all worst to the worst possible situations, right? And if what I am saying u is less than 2. Suppose I take u is equal to minus 100. Then what is mean? What is mean? Do you understand what is the problem? What is the mean?
Minus 49.
Minus, which is not member of set. So there is ambiguity, right? Do you understand this? Is it clear what is the ambiguity?
Yes, sir.
So there is a problem. When I say u less than 2, then there is no restriction. So you have to take care of this such kind of things, right? If I take u less than 2, then what is the appropriate choice for x? Because in that case, in this situation, the mean may not be member of set, right? So in mathematics, you need to logically see, this is algorithm. When we write some proof, it is algorithm, and when in future you are going to apply such kind of things in computer programming or anywhere else, and therefore when you write algorithm or program, you need to take care of such kind of things. So you have to consider all the possible cases, right? If my u is for example 1.5, then no problem, u plus 2 by 2 is member of set. In that case no problem, because 1.5 is here and I take mean, then this is mean here. In that case no problem at all, but in general there is a problem, right? So what I should take in this case? Do you understand what is the problem? First of all, do you understand what is the problem?
Yes.
Okay. This is very important thing. Unless you understand the problem, you cannot think about how to solve the problem. Okay, so this x is not the right x, right? Okay. Now what I will do, I will choose then x is equal to maximum of 1.5 and u plus 2 by 2. Do you understand what I am saying now? I will choose maximum of 1.5. Why 1.5? Now, if I choose this x, then there is no ambiguity at all. Whatever is your u is minus 100 or minus 5000. Maximum is 1.5 is always member of set, right? Then x is a member of set. Am I right?
Yes, sir.
If okay, so let me make this more clear. So this is 1, this is 2, and suppose I take u is equal to 1.23, right? U is here and 1.5 is here, and what is mean now? This is mean, u plus 2 by 2. Is it clear? Which is maximum in this case?
Mean.
Arithmetic mean, right? And therefore, whatever is the situation, your u is in between 1 and 2, or your u is very small number like minus 100 or minus 5. In any case, maximum is either 1.5 or mean. In any case, this element x is member of set. And what happens? 1 less than x less than 2. Not 1, what I want. And u less than x less than 2. Correct? Is this clear now? Is this clear?
Yes, sir.
Right. So
Yes.
why we are modifying our arguments? Because if I take the arithmetic mean, that is the problem there. There is ambiguity. Your program will not run at all. And therefore, if you use this argument, then clearly your program will run, because there is no logical error. There is no ambiguity at all. Right. And therefore, what is the conclusion? What is the moral of the story? Thus, for any u less than 2, there exists member of set such that u less than x less than 2, and hence U is not an upper bound of A. Okay, so this is clear now. Do you agree with this?
Yes, sir.
Okay, so similarly, you try to prove that. Okay, therefore, supremum of A is 2. Similarly, prove that infimum of A is 1. So, with same logic, same arguments, right? So, if you choose any one is lower bound, that is definition of set, and if you choose any u greater than 1, that is not lower bound, because you can choose some element from set which is less than u. So, you can work it out, calculations, right? Now, what is ALUB axiom? So, ALUB axiom or completeness property of real numbers. So here, in this previous example, in this previous problem, our set was very straightforward. Ki 1 is less than x less than 2. So all numbers between 1 and 2. That was our set. And therefore, easily it was, we could understand that 2 is upper bound and least upper bound, and 1 is greatest lower bound. So, but sometimes sets are very complicated, which we cannot visualize easily. Right? Sometimes sets are very complicated. And to understand this complicated situation, we need some power, mathematical power. Right? And in this previous example, any number smaller than 2 cannot be upper bound. So we need some mathematical power. We can immediately produce some element and so on. So which power we need? Arithmetic mean and so on. So that is a power we can have. Right? So to understand very complicated sets which we cannot see easily, like natural numbers we can understand, integers we can understand, or interval we can understand, right? Or finite set we can understand. But if you read further, when we develop the theory further, you can understand there are very really complicated sets. And in real life also complicated sets arises because you have some data, right? Then data can be very complicated data, right? In data science, so there is a data which is very complicated and I have to analyze that data. So you need lots of mathematics, right? So that's why we need to understand very complicated sets, right? So to deal with complicated sets, we need some mathematical power, and which the supremum infimum of such sets we cannot detect easily or cannot be identified easily. Okay, so what is completeness property or ALUB axiom, right? This is axiom. Axiom means what? Basic assumption, basic structure. So if is non-empty, subset of R which is bounded above, then A has supremum. In R, supremum in R, that is important. If A is a non-empty subset of R which is bounded below, then A has infimum. Right? Infimum has infimum means it is available in real world. Real world means in real numbers, because whatever is in real numbers, that is in real world. Everything outside real numbers is not in our world. Right? It might be in another world. So that is what the meaning of real world, real numbers, in real numbers. So that means supremum of set A exists. Supremum of A exists means supremum of A is a real number. It is some finite number if set is bounded above. Right? So every bounded above set has a supremum. Every bounded below set has a infimum. That is what the, and we can combine these two. Every non-empty bounded set bounded subset of R. Bounded means what? What do I mean by bounded?
So which is both bounded above and below.
Very good. So every non-empty bounded subset of R means it is bounded above as well as bounded below. And if it is bounded above means it has a supremum, and it is bounded means it is bounded below, so it has infimum. So has supremum as well as infimum in R. Right. So every bounded subset of R has supremum as well as infimum in R. Right. So that's how the set of real numbers is constructed. People will initially, if you read the PDF which I shared with you in the introduction of real numbers, I mentioned it. If you have a set of real numbers, if you have a set and you have a subset, then people thought that ki rational numbers are sufficient. You can fill up the line by rational numbers. Right, but people found that ki there are subsets of rational numbers whose supremum is not rational number. Right, or there are subset of rational numbers whose infimum is not rational number. So some numbers are missing, and so such numbers must be included, and those numbers are called as irrational numbers. Right, so that filling the gaps, right, the filling the gaps, that gaps were filled, and then the line becomes complete. Right, that's why these axioms are called as completeness axioms or completeness property. Is it clear? Do you understand what is the meaning of completeness? Is it clear? Do you understand?
Yes, sir.
So the rational numbers were not complete because people found some subsets of rational numbers whose supremum is not rational number or infimum is not rational number. That means the set of rational numbers were not complete. There were some missing, say there were some gaps. Such gaps are called as Dedekind cuts. Dedekind cuts. So Richard Dedekind, mathematician, proved that key rational numbers are not complete because we need more numbers. There are people said that key if you arrange all the numbers, rational numbers on the line, then line will be completely filled. But then Dedekind showed that no, this is not true. There are some cuts on the line, right? And what are these cuts? Cuts are the supremum or infimum of some subsets of rational numbers. He said that there are subsets of rational numbers whose supremum is not available there, so we should include it. Right? In that process, people fill the gaps, cuts, and then line becomes complete. And what are the gaps? Gaps are basically irrational numbers. And how many gaps are there? if you compare with rational numbers, what do you think? If you compare with the gaps and rational numbers, which is a larger amount?
Irrational numbers.
Right, so irrational numbers are very, very, very larger than rational numbers. So gaps are very huge gaps. Right. So in that sense, the property is called as a completeness property. Right. So I will tell you some set A is interval 0, 1. Now, what is this set 0 less than x less than 1? Now, is this set satisfies completeness property?
Yes.
Right. What is my set A now? I am talking about set this numbers between 0 and does this set satisfy completeness property? So I will give you set B. I will give you set x is equal to 1 by n. Okay, I will choose n greater equal to all natural numbers greater equal to. Now, do you understand where is this set? Right? Is it a subset of A?
Yes, sir.
This is subset of A. Is it
Yes.
bounded? X is bounded below. Right? Is it true? Is x bounded below?
Yes. Yes, sir.
Right. But what is infimum of x? Just we proved in the previous problem.
0.
0, which is not member of set A. You understand? What is the conclusion? This set or space, we can say now our space is this interval 0, 1, A. Then it has a subset which is bounded below, but its infimum is not in that space. That is, there is a subset of A which is bounded below, but its infimum
सर इन्फिमम 0 कसं झालं परत एकदा सांगता का?
infimum is not in A. Okay, yes, previous discussion. What is our previous discussion? What is infimum of this set? What is infimum of this set A? What is this set? 1 by n. Do you understand this?
Yes, sir.
What is infimum of that set? Okay, forget about here. I am calling A as this interval and X as this. So forget about notation A. But what is the infimum of set 1 by n? 0. That we have already proved. Right? Is it correct or not?
Yes.
And what is set X in this case now? Same set, except one element is less. I am not assuming one because I am assuming considering open interval. So that is not an issue. But still infimum of this set is 0. Infimum of X is 0. Do you agree?
Yes.
Right. And it is not in the space A. Now my space is A. Right. And I have a subset which is bounded below of this space, but its infimum is not in the same space. Okay, you think about this problem. Next time we'll continue with this supremum completeness property. But this is a Is it clear? Is it clear what I am saying? What I said, is it clear or not?